Our next section on applications of derivatives is about kinematics, study of motion of objects. So we're looking at distance, velocity, acceleration. And there's some very neat applications in calculus with these things. Okay, so we know that your derivative is the slope of your curve. And the derivative represents a rate of change of y and x. Now, in our very first unit, we talked about rates of change, and it said, well, if it takes me an hour to get from here to Portage-la-Prairie, and Portage-la-Prairie is 50 kilometers away, then I have been traveling 50 kilometers per hour. And so that would be my average speed. And then we talked about instantaneous speeds along the way being the derivative. So the interesting thing that comes out of this is if we can make a function that shows their distance traveled, if we take the derivative of that function, we'll get our velocity. So the rate of change of displacement with respect to time, that's velocity. I'm not sure why they've decided that S is the best letter for displacement. Maybe the first person. Yes. Maybe that's why. Yeah. The instantaneous velocity, if you want to find out how fast a vehicle's traveling and you've got a graph of its distance, if you find the derivative at a certain point, you will find the exact velocity that that vehicle was traveling at that point. So here's our first example. We've got displacement of a body at t seconds is given in meters by this. So here's our example. I'm standing right here. At time 0, I don't move. Time 1, how far am I going to go? 4, so I'll go 4 blocks forward. Time 2, I'm going to go up to 10, so I need to move another blocks forward, and so on and so on and so on. And that would be what this function is. Now, can you see if I start in the first second, I have to go 4 blocks. The second, I'm going to be already at 10 blocks, so I'm going to have traveled 6 blocks in this from second 1 to second 2. And the first second, from 0 to 1, I move 4 blocks. And then from second 2 to second 3, if I plug in 3 into this, I'm going to go 18, which is 8 blocks. I'm going faster and faster and faster. I mean, if I could reenact this for seconds, for the first 25 seconds, oh, I'd be going really fast. It'd be really entertaining. But I don't think we can reenact that. So what is our velocity? Our velocity is always our derivative of our time. And in this case, we've got meters per second. So at 3 seconds, if I plug in 3 for time, I'm going 9 meters a second. Would I win the 100-meter race at that speed? Not quite, eh? Because that would be over 10 seconds. It'd be like 11 seconds. I might make the Olympics. But I don't know if I wouldn't. Oh, I don't know. At 11 seconds, you're probably not making the Olympics. But if I continued to increase my speed like this, I think I could win the 100-meter dash. The initial velocity, what does it mean for initial velocity? When t is equal to 0. So I am starting out at 3 meters per second. Yeah. You can do it. You can do that to keep up with that. That's fine. You know, it'll be fine either way. And the velocity after 4 seconds, well, there I'm going 11 meters per second. And these are the questions that I find really show mathematics and physics coming together. So you got a stone, you climb up a cliff, maybe there's a river below and you like to watch the splash, and you're 122.5 meters up, and you throw this stone off the cliff, and this is the model of what happens. How fast is it going after 2 seconds? Well, this is our displacement graph. So in order to find our velocity, we're going to need to take the derivative. So we take the derivative. It's negative 9.8 t. And then we plug in 2, and we find out that after 2 seconds, that stone is traveling negative 19.6 meters per second squared. No, meters per second. Do you see the negative 9.8? Does that remind you of anything? Reminds you of gravity, right? And we're going to find out in a slide or two that the derivative of velocity is acceleration. So if you took the derivative of this one more time, you get negative 9.8. And what do we know about gravity? It's constant. It doesn't increase or decrease. It's always negative 9.8. So now if you went back to your grade 11 textbooks, of all the ones where like a ball was thrown up in the air and it made a parabola, what's the maximum height? If you would go back and look at all of those, you will notice that in front of the t squared, you almost always had negative 5. Or if it was a calculator question, they might have put negative 4.9. Because in order for that question to be accurate on Earth, gravity is negative 9.8, you're going to have negative 5 there. If you have an American textbook, you'll often have negative 16 there, because they change from meters to feet. And then they use gravity in feet per second squared instead of meters per second squared. So now you can look back at those questions and understand a little bit more about them. When is the stone going to hit the ground? So these questions, they're going to get you to think back and forth between, now which equation do I need to use for that? Do I need to use my displacement equation? Do I need to use my velocity equation? And later on, we'll be able to have an acceleration equation. Well, what do you know when the stone hits the ground? Do you know something about the velocity? Do you know something about the height? The height is 0. So then you need to use your original equation. Set your height equal to 0. Solve for t. And this is one where the numbers are so pretty. Now, solving this equation, you get t is equal to plus or minus 5. Why does only one of those make sense? Negative time? Oh yeah, I hit the ground 5 seconds ago. I haven't thrown it yet. No, that's an S. Sorry about that. Now, if we want to find the velocity when the stone hits the ground, now we can go to our velocity equation. We know that the time is 5. Plug that in, and negative 49 meters per second. What would it feel like to catch a stone traveling at negative 49 meters per second? So, you can learn from this that if someone else is up on top of a cliff and they have a stone and they say, you want to play catch? You say no. Good. We've now used math to learn something. Because in the past, someone would have found that out by trial and error, and then they don't get to learn anymore. So we talked about it already. If we take the derivative or the rate of change of velocity with respect to time, that's acceleration. So our acceleration is dv dt. Go too fast? Acceleration is dv dt. And then you could also say if you started with your displacement formula, well, then your acceleration is the second derivative. And this is Leibniz notation for the second derivative. First derivative of velocity, second derivative of displacement. So we have another example here. We've got our displacement formula. If you wanted to find the velocity after 1 second, well, then you're going to need to find your first derivative and then plug in t is equal to 1. If you want to find the acceleration after 1 second, well, now we're going to need to find our derivative of our derivative, or our second derivative, and plug in t is equal to 1. When is the acceleration 0? And what does that mean? Here. What would that mean? If I'm going this way, I'm accelerating. If I stop and I start going backwards, my acceleration went from going forwards positive to going backwards. So I'm changing directions at that point. Okay. So I'll let you try this one. Again, the kinematic stuff, it's not that bad. It's not that hard. Usually simple questions, just moving from velocity to acceleration. What does it mean with the bodies at rest? Velocity of 0. So you need to find the derivative and then set it to 0. Find the values of s at these times. Well, then you would be plugging in both 3 and 1 into your original equation. And then finally, finding your acceleration at these times, you'd have to find your derivative of your velocity and plug in those values.